Hi, Jim Heffron. These are my lessons in Calculus 1. And what we're going to talk about today is exponential growth and decay. So we're again thinking about the derivatives, trying to understand some things on the basis of derivatives, and also trying to use those things to help us think more clearly about what derivatives are about. So this will be fun. Let's get started. Okay, let's see now. The easiest way to understand exponential growth and decay is to think about interest. I expect that interest is a familiar case to everybody. Maybe a person might need a prompt, but everybody has seen the formulas before, so I'm going to go through them relatively quickly. So for simple and compound interest. Simple interest is where you have a principal amount of money invested for a number of years and at some rate. And the simple interest is the straightforward formula P times 1 plus RT, where if you leave the money, say, for 5 years, then you get 5 times the amount of interest as if you leave the money for 1 year. If instead the interest gets assessed n times a year, then what you're looking at is compound interest, because what's happening is that after you leave the money for the first period, now you have slightly more money than you had before, and so you're getting interest on that extra money. So you're getting interest on the interest in some sense, and so it's compounding, it's growing, it's building up on the basis of having basis of it having built up before. So that's the familiar formula: P times 1 plus R over N to the NT. And again, I expect that all this stuff is old hat for a person watching this, but nonetheless, maybe you can use a prompt. So my example is deposit $1,000 for 5 years at 4.25%. And really the major point of this example is you got to convert that to a decimal. And I'm compounding quarterly. I did simple interest and compound interest, and I showed the dots at every quarter. So these are the filled in dots, and these are the open dots. And of course, the compound interest here, the compound interest case gets you slightly more. And the reason is because you're getting interest on the interest. With simple interest, you're just getting interest, but with compound interest, you're getting interest on your interest. In some ways, it's easier to understand the numbers than it is to understand the picture. So if you look at the two cases, what you'll see is that the compound amount picks up steam. At first, the difference is very small, but then after a while, the difference gets to be, this is not overwhelming. After 5 years, you're looking at 22.87, that's dollars and cents, so almost $23. But nonetheless, you're picking up a kind of momentum with the compound amount. Okay, so compound amount gets you more because you're seeing growth not just in the original principal, but also growth in the money that you got previously as interest. So the obvious question is, what happens when you compound more often? One of the obvious questions. If you compound quarterly, is that better than compounding, every 6 months? If you compound once a month, is that better? If you compound once a day, is that better? So the obvious thing to do is make up a table, and so I did. I made up a table here going from 1 compounding a year up to 1 million compoundings a year, and then I calculated the amount. Now, what do I mean by amount? And the simplest principle to put on deposit is $1. The simplest number of years is 1 year, and the simplest rate is 100% interest, so I use those numbers. And you can see what happens over there in the right-hand column. You're looking at the amount that you get does indeed grow, but we're familiar with how this works. Now, it grows in a way that is bounded. That is to say, there is a limit. When you take larger and larger n's, there is a limit to the amount of growth that you see. So as n grows, the amount grows, but in a bounded way. That limit is Euler's number, called E. So the definition of E is just simply that it is the limit of the right-hand column above. Okay, so that's the right-hand column above. So you get 2.71828. I wrote up all these decimal places just to try to give a person some sense that it is like pi. It is an irrational number. Goes on and on without repeating or terminating. All right, but 2.718 is a perfectly practical approximation. Just like, for pi, you might say 3.14. 2.718 is a perfectly good approximation here. So the formula for what happens when n goes to infinity is here. It's a equals pe to the rt You call that continuous compounding, and people will say that out loud as PERT. I probably will say it out loud. I'll say, well, apply the familiar PERT formula. The proof of that is not very hard, so here I'm going to go through it. The idea is that we're going to fix the rate and time and just simply take the limit, fix the rate and time, and just simply take the limit as the number of compoundings goes to infinity. That's precisely what we're thinking of when we're trying to think of compounding continuously, is compounding sort of every instant. Now, to get from the top of the page to the bottom of the page, there's only one spot that would give a person trouble, and that is you'd be walking around looking at this and looking at this limit and trying to say, well, how am I going to connect it to the formula that's up there? And so at some point you would hit on the idea that you need to introduce the definition of E somehow. So you need to change what's in square brackets from 1 plus R over N to 1 plus 1 over M, because that's the definition of E. And so you would introduce a variable M with the property that R over N is 1 over M, and now you're set. Now you thought of the right thing, so good. Then let's see, N equals MR. That's to say N and M are proportional, where R is the constant of proportionality. Since R is fixed, when N goes to infinity, M goes to infinity. So I can replace the expression that's here with the expression that's here. N goes to infinity gets replaced with M goes to infinity. 1 plus R over N gets replaced with 1 plus 1 over M. And where it says N, I replace that with MR. And now I just simply use the laws of exponents to write R times T on the outside there. And now I'm remembering from up here, that R and T are fixed, so they don't depend on M. So they don't change when M changes, so I can bring them in outside the limit entirely. And now I recognize what's inside those roundy brackets as the definition of E, and I'm looking at E to the RT. Okay, so not hard, although there is one spot that would, a person would not see at first glance, but it isn't super hard. So a lot of times with these, a person wants to have a concept, wants to have sort of a takeaway where you're saying to yourself, what's happening with these? This is X. And the answer is what's happening with compound interest is that it's feedback. The way that interest works, every time you're compounding, you get more money. And because you have more money, then the next compounding you get even more. So feedback is how we summarize. How we summarize that phenomenon. It's where the rate of change is governed by the current value of the function. That's what feedback is. I mean, everybody has been at a concert or some other venue where you have a microphone that's too close to the loudspeaker, and some noise from the loudspeaker gets into the microphone, gets sent to the amplifier and made louder, and now it's a bigger noise coming out of the speakers and going into the microphone and getting amplified, and an even bigger noise like that. So when the rate of change is governed by the current value of the function. So it can be that the rate of change is 10% of the current value of the function. It could be that the rate of change is minus 10% of the current value of the function. But surely the simplest case is where the rate of change is equal to the current value of the function. That is to say, it's 100% of the current value of the function. And in a continuous context, that's you would say that the rate of change is the current value of the function. You're looking at that formula. Okay, so the sort of takeaway, the understanding of what's happening is you look for exponential formulas to apply in cases where there's some kind of feedback situation. Sometimes the formula that f prime is equal to f, this feedback formula, sometimes people feel like it's a little weird, isn't it? And it does seem to take some getting used to, that f prime equals f. So I have this graph to illustrate what's happening. Okay, so on the graph, I'll start with the upper of the two here. On the graph, we are at x equals 1. On the upper of these two, at x equals 1, you plug x equals 1 into the formula f of x equals e to the x, and you're looking at 1 comma 2.718. At 1 comma 2.718, the tangent line, the rate of growth, the slope of the curve, is 2.718. Tangent line, slope is 2.718. And we already know that a slope of, etc., etc. We already know that a slope of 2 or 3 is going to be pretty steep. Whereas down here at -2, when x equals -2, you plug -2 into the formula f of x equals e to the x, and you get 0.135. I just plug it into the formula. I just plugged it in my calculator. And a slope of 0.135, I mean, it's positive, it's going up, but it isn't really going up a lot. So exponential functions, and e to the x is no exception, have this characteristic upward sweep where they seem to just take off suddenly. And I mean, I remember, driving home from work on March 13, 2001, and they were talking on the radio about COVID. 2020, and they were talking about COVID, and that's what everybody was afraid of, is that there would be a couple of COVID cases, and then suddenly everybody would have COVID. So there's this characteristic upward sweep to the exponential functions that the person recognizes the graph. Again, I'm a little concerned that we first saw the derivative of e to the x, first saw the derivative of exponential functions back when we were doing derivatives of polynomials, and we kind of gave it short shrift because we were interested in using the derivative in order to do the product rule. We needed functions to do the product rule with, and so we didn't really give it the sort of concepts that it deserved. So I'm trying to show this in a number of different lights. Okay, so to make up for that. So I'm going to take the derivative of e to the x from the difference quotient definition to try to give a person who says to themselves, well, what happens when you just plug it in? So here we go. Limit as h goes to 0 of f of x plus h minus f of x over h. So there I put in x plus h and I put in x. Okay, good. Of course, an exponential function, if it says e to the x plus h, that's the same thing as e to the x times e to the h. Okay, good. And you see that e to the x factors out. And since e to the x doesn't have any h's in it, you can in fact factor it out of the limit entirely. And I'm left with a limit as h goes to 0 of e to the h minus 1 over h. And now I'm not going to go through a proof that that limit equals 1, but I got the computer to draw a graph of e to the h minus 1 over h. And, absolutely, a proof is necessary. That's absolutely right. But in this course, we sometimes feel that it's okay to say, it's clear that, and come on. It's clear that, look at the graph, it's clear that the function has a limit of 0, that this graph has a limit, at h equals 0, this graph has a limit of 1. I misspoke. At h equals 0, this graph has a limit of 1. It's perfectly clear, and I'm not going to give the proof of this. But I think that a person can walk away from the graph at least saying, well, it really is true. So I think a person can feel like this is another example of a function that has a hole in it that isn't sort of a made-up phony hole, like when you have x plus 3 times x minus 3 over x plus 3. This is a genuine hole, but come on, the limit is actually 1. It's pretty clear. Okay, so having done the derivative of e to the x, having repeated the derivative of e to the x, and having done done it in a couple different ways and tried to give a conceptual sense for what's happening, I want to do a couple of applications. So all of these applications are characterized by some sort of feedback circumstance. So you deposit money at an annual rate of 4% compounded continuously, and how long until the money doubles? Now, a person who first reads the question might say, well, it depends on how much money it is. No, it doesn't. So the point of this slide is, I don't have the calculations up yet, but it's what I just said, is that how long until the money doubles does not depend on how much money it is. So how long until the money doubles? Ask this formula asks that question. You start out with P, you end up with 2P. What is T? And instantly you see that the p's cancel, and so the p does not matter. It doesn't matter whether you start with $1 or $1,000,000. The time to double is exactly the same. Of course, I want to find what the time to double is, but that's a big point. The time to double is exactly the same. It does not depend on p. All right, so obviously now we have a variable that's in the exponent, and so I solve for that by taking the logarithm of both sides, logarithm of the left and logarithm of the right. You remember that natural logarithm and e to the cancel each other. So natural logarithm of 2 and 0.04t. That is to say, if you take the natural logarithm of e to the 0.04t, then they cancel each other. Have one parenthesis too many. There we go. Then they cancel each other, and natural logarithm and the e to the cancel each other, and you just get the 0.04t. And natural logarithm of 2, my calculator told me it was 0.693, divide through by 0.04, and you end up with 17.33 years. So 4% compounded continuously takes a while to double. It doesn't take lifetimes, but it takes a while. If you imagine that your working life is 35 or 40 years, it takes half of your working life. So for exponential growth, the doubling time is independent of the amount. And the formula for doubling time is just basically the calculation that we just did. But the interesting thing here is that the doubling time is independent of the amount. If I tell you the rate, you can calculate the doubling time, or also if I told you the doubling time, you could calculate the rate. In the formula that's on the bottom there, if I told you t, you could calculate r. So I'm going to have example. This is not compound interest, but it's exactly the same idea. Bacteria culture grows according to the PERT formula. It happens to be the case that when you first, sort of scrape the culture onto a petri dish, the population was 400. After 4 hours, it was 25,600. So that's fast-growing population, and we want to find p. And now, of course, in the PERT formula, p is what happens if you plug in t equals 0. So to find p, all I need to do is to plug in p equals 0, and it comes out to be 400. Okay, so that's the initial population. Find r. So to find r, you've got to somehow use growth information. So I can't use the initial. I need to somehow use the growth information. All right, so do you see here that this is the growth after 4 hours? This is the initial population, and there's the time equals 4. And I just got to solve it. So to solve it, I just did what I did here. You could probably do it different ways, but I divided both sides by 400, and then I took the natural logarithm of both sides to get at the exponent. Getting at the exponent, take the natural logarithm of both sides, and then I ended up dividing by 4, and when all the smoke clears, I got 1.04. Okay, so r equals 1.04. Then it says predict the population when t equals 5, so I plugged in t equals 5 into the formula here, the PERT formula. T equals 5 with the numbers that I now know. I know that r is 1.04, I know that capital P is 400, and when I calculated, I got 72,509. And then find the doubling time. You can either use the formula from the prior slide, or I'm not very good at memorizing formulas. So I just did the simplest thing, which is I went back to 2p is equal to the formula here, the PERT formula, and I cancel the p's and do the division, and I end up with 0.67. Okay, so here's a question that looks a lot like the last one, except that it doesn't say f of 0 for the starters. It says f of 3, and the other one is f of 5. Okay, so how to do that? So we got to find r, and the hint is compare the two populations in ratio. We got to figure out what is r, and the right thing to do is to look at somehow the growth between 190 and 9100. So 9100 and 190 is 9100 over 190 is PE to the 5R over PE to the 3R. Cancel the P's, so kind of a theme there. E to the 5R over E to the 3R, you subtract the exponents, right? E to the A over E to the B is going to be E to the A minus B. So I get 90, 100 over 190, whatever your calculator says that is equal to e to the 2r. Take the logarithm of both sides, and you end up with r equals 1.93, approximately. So once you know r, then you can use it to go back and find p, figure out p. So I took the f of 3 equals 190, but I could have taken the other one. I just had to pick one. That's the one I picked. So 190 is e to the 3 times 1.93, and then the rest is just a question of coming up with the calculator. E to the 5.79 gave me 327.01, and I divided through it, and I ended up with about 0.58. Okay, so a couple of examples of growth, one that involved interest and one that involved, bacteria in a colony. And again, you're seeing this feedback. For example, with bacteria in a colony, the more bacteria you have, the more bacteria there are to reproduce. And so now there's even more growth kind of stuff. Exponential decay. So radioactive material loses exponentially instead of gains. So with money in the bank account, you hope that it gains. Same thing with bacteria in the petri dish. With radioactive material, it loses exponentially. So if you have only a little bit of radioactive material, a tiny, tiny fraction of a gram on your desk of radioactive material, that will show fewer clicks on the Geiger counter than if you have a big pile of the same kind of radioactive material, just because there's less of it. So the bigger the pile, the sort of fewer clicks you have. That is to say, that the less your material is converting into something else. So radioactive material loses instead of gains, so it has a negative R, but everything else is pretty much the same. Instead of a doubling time, it has a half-life. But everything else is pretty much the same. So one example here, radium-226 has a half-life of 1,590 years, and we're going to calculate R. Okay, so I wrote down, again, a person can memorize a formula, but I personally think it's easiest to remember PERT and use it for all the purposes. So you have half of P after 1,590 years. Cancel the p's, and again, the lesson of canceling the p's is that it doesn't matter what p is. You're going to get the same answer. You'll end up with r equals whatever it is at the end without p having any effect. It turns out that when you do the arithmetic, and I'm not going to go through the arithmetic because it's familiar from the other examples, you come up with a negative number, and the negative sign signals decay instead of growth. A negative rate is decay instead of growth. That's all, but the kind of steps that you go through, take the logarithm of both sides, those steps are all the same. The halving formula is, doesn't it look an awful lot like the doubling formula? The halving formula is the natural log of a half over r, and sometimes people tell me, they'll say, well, in my chemistry class, we memorized, fair enough, natural log of a half is, so ln of a half is ln of 2 to the minus 1 power. Do you remember what ln does to power? So that's minus ln of 2. Okay, so sometimes people say they memorize one version or the other, and there you go. Last example, chromium-51 has a half-life of 28 days. Find R and find out the amount left after 3 years if you started with P equals 0.23. Half-life of 28 days it's decaying pretty rapidly. I mean, not super rapidly, but pretty rapidly. The half-life information gives this. I decided to work in years because the question says left after 3 years, but that gives you some ugly fractions. Anyway, 28 days is 28 over 365.2425. I looked up the number of days in a year. Anyway, that's what Wikipedia told me. So I have a 1/2. Oh, it says P naught. It's just supposed to say P. Sorry. Oh, what am I doing? Just supposed to say P. Sorry, a little typo. 1/2 P, P e to the R times, I made the time be 28 days, and cancel the P's. So again, we're seeing that the fact that the P's go away means that the P's have no effect on the final answer. And now the arithmetic is all the same except for this weird fraction here. And when I do the calculation, I got r equals negative 9. So again, negative 9.042. And again, the significance of the negative is that it's exponential decay, it's radioactive decay, rather than radioactive growth. Or excuse me, rather than exponential growth. And then finally plugging in 3 years. So I did that ugly fraction so that my units was years. And it turns out that you have a tiny, tiny amount, 10 to the minus 13. If your half-life is 28 days, then about every month you're going to be half of what you were before. Over the course of 3 years, that's 36 months. So half, so it's a half times a half times a half. Ooh, boy, that gets small. Okay, very good. So again, we saw originally saw the derivative of e to the x back in the first section of chapter 3, and we at that point only saw it. I really just gave you a formula, really, and the purpose of that was because we wanted to do product rule, and we needed more than one kind of function to do product rule, and that's not really a good reason, but it's a reason. That's what we needed. So here I've been trying to be careful to show the derivative of exponential functions in a couple of different ways, some conceptual, some sort of mechanical, but trying to make up for the fact that I simply gave you the formula a couple of sections ago. Okay, very good, very good.